Hi. In the previous videos of this unit, we introduced the idea of the LU decomposition and discussed its derivation as a representation of Gaussian elimination. In this video, we're going to focus more on how we can use the LU decomposition as a tool to simplify the solution of linear systems, especially when we have multiple right-hand sides. We're going to begin with an introduction to a description of a very simple way to generate L. And this is really central to being able to effectively use LU decomposition, especially by hand, because it's going to allow us to very easily write down the matrices we need. We remember that LU decomposition really is a representation of a process outlined by this schematic. We start with a matrix A. We do all of the row exchanges that we might need up front, giving us A prime. This is represented by a matrix P, a permutation matrix P, where A prime is given by the PA product. Okay. Once we have A prime, we then do elimination, forward elimination to an upper triangular matrix, where we only need to do elimination steps. We do not need any row exchanges. And this can be encapsulated by U equals L inverse A prime, or A prime equals LU. Putting that all together, we have PA equals LU. Central to this is that L is a lower triangular matrix that really reverses the process of elimination. We apply L to U and we get back A prime. Because it is reversing elimination, we can think of it as the inverse of the forward elimination matrix, which is L inverse. And we can equally think of it as a product of the inverse of the forward elimination steps, or the matrices corresponding to the inverse of the forward elimination steps. If we take a look at this product a little bit more deeply and think about what form these elementary matrices have, what form the inverse of the elementary matrices we have, we remember that because we've done all the row eliminations up front, or the row swaps up front, and we are limiting ourselves to standard Gaussian elimination where we don't do any extra row scaling, every elimination step is of the same general form, subtracting a scalar multiple of some row from another and replacing that target. To reverse that step involves simply changing the sign but otherwise applying the same operation. How do we reverse subtracting a scalar multiple of row j from row I? We add that same scalar multiple of row j back to row I. Because of this equivalence in form with just a sign difference, makes it very easy to directly write down the elimination matrix for the forward step and the inverse elimination matrix very, very simply as we perform elimination. Let's take an example to see how we do this. Imagine that we have a prearranged matrix here, PA. We do not need to do any row exchanges. And think about following standard Gaussian elimination through this matrix. We would start in the upper left corner, use the first entry of the first row as a pivot to eliminate downwards. This is achieved by subtracting 2 times the first row from the second and adding 1 times the first row from the third. The elimination matrices for each of these forward steps are written down in a very, very simple manner. We identify the row we're working with, say row 2, and the row we're using as a pivot, I. target row 2, pivot row I, we look in, pivot row 1, we look in row 2 and column 1. Then in that space, we enter the coefficient we have here. For the second elimination step, we're working with target row 3, pivot row 1, so we look at row 3 for our target, column 1 for our pivot, and we enter +1, our coefficient, in that entry. This is done in a background of the identity matrix, 1s on the diagonal and 0s everywhere else. For the third step, we do exactly the same thing. This should be a 3. We would move over a column and down a row. This pivot in position 2, 2 to eliminate downwards. How do we do that? We add 3 times the second row from the third. The elimination matrix corresponding to this operation is equally easy to generate. Target row 3 makes us look at row 3. Pivot row 2 makes us look at column 2. We find the corresponding entry here, and we put in the coefficient +3. Very simple. Now, what's very cool is that we can find the inverse of these matrices with absolutely no additional work, simply because the inverse operation is the same fundamental operation, just changing the sign. And so to reverse subtracting 2 times the first row from the second, we add 2 times the first row, and the only difference is that we change a sign in that position. To find the inverse of the second step, where we were adding the first row to the third, we subtract the first row from the third. We simply change the sign of the corresponding element here. And if we were adding 3 times the second row to the third, we change that we reverse that by subtracting 3 times the second row, and we simply change the sign in the corresponding entry. So it's just as easy to directly write down the inverse of these matrices as we go through elimination as it is to write down the forward matrices. Now, there's a really interesting thing that happens when we take the product of these inverse elimination steps to find L. What we will find is that the product has all of the same scaling terms in exactly the same place. It's almost like we just superimposed the the elimination matrices, ignoring the background zeros. So what do we mean by this? So how would we generate L from those matrices we discussed before? We would take the product of the elimination matrices, and we apply them in the reverse order, applying E3 first, the inverse of E3 first, then the inverse of E2, then the inverse of E1. But when we write them down left to right, they appear in order 1, 2, 3. So our inverse of our first matrix, inverse of our second, inverse of our third. We can just sort of quickly walk through so that you see that the product really is. What does this first product? We multiply this first row, 1, 0, 0, by each column. That's just going to pick out this first row. So this is going to give us 1, 0, 0. The second row multiplication here is going to multiply here. 0, 1, 0 is going to pick out the second row. So that's actually going to be unchanged. If we multiply these two, so just to be clear, we're focusing on this product. This product gives us 1, 0, 0, 0, 1, 0. And for the last product, negative 1 times 1 plus 0, 0, negative 1. For the second entry, 0 plus 0 minus 3. And for the third entry, negative 1 plus 0, 0 plus 0 plus 1. And if we then now multiply this matrix by that product, the first row, 1, 0, 0, has the effect of picking out the first row, so we end up with the same. Similarly, the last row, 0, 0, 1, has the effect of picking out the last row from this product, which is what we see here. And the central row, the second row, we have to take another look at. 2 times 1 plus 1 times 0 plus 0 times negative 1 is plus 2. 0 plus 1 plus 0 is 1, and 0 plus 0 plus 0 is 0. This. Now, let's take a careful look at what this looks like. This result highlights exactly what I meant. Our product has 1s on the diagonal. It's lower triangular, so all of the entries above the diagonal are 0. And what are the entries below? We have a 2 in the second row, first column. We have a negative 1 in the third row, first column. And we have a negative 3 in the third row, second column. We've constructed this matrix simply by taking all of these entries and putting them in the appropriate place in the product. Right? This only works because of the appropriate multiplication. If we take the forward elimination matrices and try to compute the combined forward elimination matrix by doing E3, E2, E1, we will not get the same result. We would actually get mixing of terms. But it is the L that we're actually interested in, and so we can use this trick, if you will. The general procedure is outlined right here. Given some m by n coefficient matrix, right? M rows, n columns, and there's a slight error here. We create an m by m empty matrix that is going to be L. We have to have the same number of rows in L as we do in A, and L has to be square. The first thing we do is we put 1s along the diagonal of L. So we sort of construct a placeholder matrix, M by M, and we put 1s everywhere along the diagonal. And we know that this is a lower triangular matrix, so we fill everything else up with zeros. Then we apply Gaussian elimination to A, converting A to U. And with each elimination step, we note which row is the pivot row. And we'll call this P. Then we fill in that column of L, whichever column we're using to pivot, and we fill it in with the multiple of the pivot that was subtracted from each row below it. That is, we're going to apply a standard operation of subtracting some multiple of the pivot row from a target row K. And how do we fill in the appropriate entry in L? We go to row K, column P, and place in that entry whatever this scaling factor is, noting that what we're looking at is a subtraction in the standard operation, and the entry we put in is the unnegated coefficient that we're going to use there. We also have to be careful to make sure that in the cases where x equals 0, that we actually skip a step in the elimination. We do need to put in the appropriate coefficient of 0 there so that we have a complete matrix. Probably the easiest way to visualize this is just to do this. I'm using the same model matrix that we had before. Right? The steps, so what do? We have a 3 by 3 matrix that we're starting with. We create, so 3 rows, we create an L that is a 3 by 3 matrix. We put 1s on the diagonal and 0s in the upper triangular block. Then we take our first step of Gaussian elimination, eliminating downwards. We're in pivot row P equals 1, and so the first thing that we do is we fill in the appropriate entries of the first column, P equals 1, and we put in the entries of -2, sorry, not -2, we're subtracting 2, so we put in +2. We're subtracting -1, and so we put in a -1. We then move over to our next elimination step. Our pivot is now P equals 2, which means we're going to fill in our P equals 2 column. Here we have a single operation. Adding 3 times row 2 is subtracting -3 times row 2. We're in, put a -3 in this position. This is L. Right? We can summarize that this this original matrix PA is equal to a product of the L that we generated by simply filling in this matrix as we went through the steps, and the U that we end up with at the end point. And you can double check that that actually works out. You do, in applying this, need to be careful about doing row exchanges. Remember that the direct approach to finding L, and in fact, LU decomposition as a whole, only works when there are no row exchanges applied during the elimination. So row exchanges need to be done first. They need to be applied to the matrix as a sort of a preconditioner to prepare it for LU decomposition. We then can move forward. If you do need row exchanges and they show up in the process of elimination and you're trying to do an LU decomposition, what do you do about that? Well, there's 2 things that you can do. One is what I would recommend as the best approach if you're solving problems by hand. It's a little bit more work, but it's a very straightforward thing to do, and it avoids errors. Perform forward elimination to identify any row exchanges that you're going to want to apply. Are you going to need to apply row exchanges? If you are, apply them. Go back, apply them to the original matrix. Now that you've done that, you're ready to repeat forward elimination to generate L. Why is this more work? Well, you have to go through the process of forward elimination to identify the row exchanges. Then you need to go back and repeat forward elimination in order to generate L. So it certainly is more work, but Forward elimination is something that is very straightforward, that you know how to do, so it's an easy thing to do, even though it is a bit more work. There is another approach. This is how you would do things if you actually wanted to implement this approach. It's less work because we're not going to end up redoing Gaussian elimination or forward elimination. However, it's pretty error prone by hand. You have to be very careful about what you're doing for this to work. And this is an idea where essentially when we reach a row exchange and we have to swap rows, we think back through the sequence of operations that we've already done and adjust the positions of L, adjust the values in L such that we reconstruct the right L as if we had applied that row exchange up front. This can be done. There's a well-defined process for doing so. Again, because it's easy to make mistakes in doing that, it's really a process that's best reserved for a computational solution where you would program it and double check and make sure everything was perfect and then use it rather than as a technique to do things by hand. This is how you would do things by hand. It's also not something I'm going to ask you to do very often. Fundamentally, LU decomposition really isn't a tool for by hand calculations. It's a tool for computational solutions. But we will go through a few examples and some practice so that you understand really how this works. Okay. Now that we have an easy way to generate L, just essentially writing it down as we carry through forward elimination, and of course we have U because U is the end point of forward elimination, we can start asking, how do we use the LU decomposition? First of all, let's think about some checkpoints. We've discussed before how at the end of forward elimination, we have all of the information we need to know what kind of solutions we have. We won't know the solution until we apply back substitution, but we know at the end of forward elimination if we have a solution, if it's unique, or if there are multiple solutions. So we can apply these checkpoints simply using the U matrix as the endpoint of forward elimination. If you remember here that U is the coefficient matrix in echelon form, not an augmented matrix. Okay. If U has no zero rows, then we know that the system must have a solution for every possible right-hand side. Why is this? Well, what would cause a inconsistent system? What would lead us to having no solution? It would be if we started with a B augmented matrix and we converted this to some U and some modified right-hand side. If the U block was all zeros and we had something not equal 0 on the other side, we wouldn't have a solution, right? But necessary for this to happen is all U's in the, all zeros in the U block. If we don't have any 0 rows in U, every right-hand side must have at least one solution. If U has a pivot in every column, that is, there are no free variables. Every column is the leading entry for some row. If this is true, then the solution must be unique. Putting this together, if we have no 0 rows and a pivot in the column, we have a unique solution for every right-hand side. This characterizes a non-singular square system. If a square matrix has no zero rows and a pivot in every column, it's singular. Also for square matrices, if there are no zero rows, there must be a pivot in any column, or vice versa, to characterize this. For non-square matrices, however, these really are independent checkpoints. Are there zero rows? If there are not, we have a solution for every right-hand side. If there are, there will be some right-hand sides with no solution. Is there a pivot in every column, or are there no free variables? If there are free variables, we have multiple solutions for the right-hand sides that happen to have a well-defined solution if there's also zero rows. Okay. So we have our checkpoints built in to U. How do we actually then move forward and find solutions if they exist, or find the right-hand sides that wouldn't have solutions? I want to emphasize at this point, the LU decomposition exists for every matrix, square or non-square. That means it can be applied to any system. Very generalizable. Our general linear system, AX equals B, and our general LU decomposition of PA equals LU. How do we use this? Well, let's think about, first of all, we have a PA here, so if we multiplied both sides here by P, we'd have PAX equals PB. But PA is LU, so we could substitute the PA. This gives us LUX equals P times B. This form can be broken down into three individual pieces. One that's really just a reordering, and two that are asking us to solve a system. First, we might say define a B prime equals P times B. Remember, P is simply a permutation matrix that reordered the rows of A. If we apply it to B, all that is doing is reordering the rows of B to match the reordering that we did in A. If A did not need any row exchanges, if we had no row exchanges in our LU decomposition, we can skip this step. This gives us B prime, the same B, just with reorganized rows. Once we have that, we can take this LUX equals now B prime, and as a placeholder, put UX equals C. U times X is, of course, a vector. And this gives us LC equals B prime. Well, we know B prime, we know L. We can solve this lower triangular system. LC equals B. Because L is lower triangular, this is an easy and fast thing to solve. We'll see how in a moment. This will also always have a unique solution because L is singular. We know L is square, and we know it is singular because it is constructed from elimination matrices that are all non-singular. And so L, we have a non-singular invertible matrix. This will always have a well-defined solution. Once we have found our value for C, then we have this last piece. C had been substituted. We had made this essentially a definition that C was going to equal UX. And so now that we've found what C must be to satisfy LC equals B prime, we now can solve for the X that would satisfy C given us this. Again, note C will always be unique because of the non-singularity of L. We now have an upper triangular system, UX equals C. We know C. We know U. We can solve this with back substitution. Excuse me. Now, U does not necessarily always lead to a unique solution, or even to any solution. If C happens to have a non-zero entry where U has a 0 row, this is what tells us that we have no solution. How do we distinguish no solution from a solution? In the case with U as a 0 row, we have to find C and look at the corresponding entry. If U has free variables in it, then the solution X will not be unique, and our solution will have to be a general solution in parametric form. But we know how to do that. So perhaps the best way to understand this is to go through a quick example. Imagine solving the system AX equals B for a given right-hand side. I'm writing this with a transpose just so that I can write it in a row here as opposed to a column, where we're not actually given A, but rather we're given the LU decomposition of A. PA equals LU, where this is our P, this is our L, this is our U. How would we go about using this? We're always going to focus on our original system, our decomposition, broken down into 3 steps. Find B prime, find C, then find X. Our first step, solving for B prime, is as simple as multiplying this column by this permutation matrix. Right? Multiplying by a permutation matrix is not the same amount of work as multiplying by a regular matrix. It's just a reordering of the entries. The first row brings us the last column, so 2 moves to the first position. The second row pulls out the first, so we move the first entry to the second. The third row pulls out the second, we move the second to the third. Apologies, my throat's a little bit dry. In the second step, now we have B prime. We want to solve this system. How do we solve a system? Right? We know how to solve linear systems. We start with an augmented matrix, our coefficients L, our right-hand side B prime, and then carry through to solve the system. It's easy to do this because of the structure of L. It's lower triangular. That means one forward sweep gives us our final answer. Using 1 as a pivot to eliminate downwards, that eliminates these entries. We then move over using 1 as a pivot to eliminate downward, gives us our final answer. Now, because L was square and non-singular, we expect that we will end up in a situation with the identity matrix and a well-defined C in the last column. This should always happen. If in this process you end up with 0 rows in this block, something has gone wrong, right? Because L should be non-singular. Now that we've found our C, we can solve the last equation. Same approach. Generate an augmented matrix with U and C. So this last column is taken directly from here. Our U was given to us. And we solve this problem through Gaussian elimination. Because we already have a U, there's none of the forward elimination steps. we immediately start back substitution. So we start down at the bottom row, the last pivot, scale it to be equal to 1, and use it as a pivot to eliminate upwards to zero out this column, adjusting the right-hand side appropriately. Then move up to our next pivot, scale and eliminate to take us back here. In this case, we happen to end up with an I in this last position. That tells us that the final answer we get is a unique solution, and we can simply read our answer off from this column. We knew that we were going to get a unique solution because U had 3 pivots for 3 variables and no 0 rows. So we expected that. Although we expected it in this case, other U's may give multiple solutions, no solution, and so on. So we've explained how LU decomposition can be used in this kind of 3-step process for solving a system, where each of these steps is much simpler than full Gaussian elimination. I think it's helpful to try to visualize this in the context of the full problem. What we really have done here is we've started off, if we think about how would we apply Gaussian elimination to solve a system for a particular right-hand side, we start with our augmented matrix. We can apply our row exchanges up front. That would lead us to an A prime. I'm sure I should have a prime here, sorry. An A prime and a B prime, simply reordering the rows. This is captured, this process is encapsulated in P, and so for a new right-hand side, we don't need to bother doing this with A. We can just directly find what B prime would be by using P. After row exchanges, we apply forward elimination. Forward elimination moves us to an upper triangular matrix version of A, the echelon version of A prime, and a new right-hand side, a modified right-hand side that we'll call C. This process is encapsulated by L. So rather than needing to apply forward elimination to a new augmented matrix for a new right-hand side, we can directly find what C must be by using L. LC equals B prime. Solve this system, we get C. Right? So these first 2 steps, the not always necessary reordering and the solving of the lower triangular system, really are simply giving us the right-hand side for a arbitrary initial right-hand side, the right-hand side that matches U, that's in the right form that we would have gotten if we had carried along as part of an augmented matrix. The fact that this is really what C is also means that we could find C simply by applying the steps of forward elimination, writing them down as sort of a sequence of things that we did, and applying them only to B rather than to the whole matrix. I think it's easier to conceptualize this as being stored in L and P, but you ought to get the same result. Once we have our upper triangular form, we would apply back substitution to a reduced row echelon form. Okay? When we have a unique solution, that would just give us our answer X. When we have a non-unique solution, this contains everything we need to solve the system, and so on. Okay. What does this last back substitution step really correspond to? it corresponds to solving the system of ux equals c, as if we had skipped all of these steps and we're starting here, and that's what we do in this third step. Right? And so what LU decomposition is really doing is it's giving us a quick way to reconstruct the needed right-hand side for any given right-hand side, the right-hand side that we need to start back substitution, and then we're left only with the problem of solving back substitution. Hopefully that's given you some understanding, some insight into how we can use LU decomposition to solve problems. There will be an accompanying video where we go through a few more worked examples of how we find the LU decomposition for an arbitrary matrix, and how we, in a second accompanying video, how we use the results of LU decomposition to solve systems. Again, to give more practice if everything isn't quite clear from the video we just finished. Thank you, and goodbye.